All right, so I am diving back into the Geth Codebase. I've got my terminal open, and today I want to have a look at the peer-to-peer layer, which is what I assume is going to be super scary. Now, there is already like a lot going on in here, and if I do like a list in here and just sort of look through the file sizes, I'm kind of like thinking that there's gonna be a big one that's got like a good chunk of it, but like there's 18 kilobytes there, 31 kilobytes for the server, which might be a good place to start. But also ENR, like Ethereum node network, so peer-to-peer ENR, because I assume the way that the peer-to-peer network layer works is that the server maintains a big list of peers, and those peers are like built dynamically. So you start off with a couple seed nodes that their Ethereum Foundation probably runs, and you go ask them for who they know, and they send back a list of like people they know, and then you ask those guys who they know, and then you build this big list of like computers who are all on this peer-to-peer network. So I assume there's a big list, and that list is of the peers. But I don't know where that list is, and I don't know what that list is called, and I don't know what the list is of. However, something called Ethereum node records kind of gives me like a little bit of a like a hint that might be the right way to look for this. So Ethereum nodes discover each other through this node discovery protocol. We relay node identity public keys. So we've got public keys for each node, and their IP address and 2 port numbers. Why do they have 2 ports? The specification restricts discovery P4. So if we go into, first before we do, to go into discover, is there a 4 and a 5? Yeah, we've got a 4 and a 5. There's a table there. That's interesting. ALH. There's a 20 kilobyte file there for table, and there's 24 for version 4 UDP, and then 25 for this one. So maybe this UDP and maybe this table is a place that we want to look at. What's this enode though? It's an Ethereum enode. What is an enode ID? Enode URL format. That could be interesting. Can it be described with a URL scheme encode or enode? So it's a hex. Username portion of the URL. Right, so this at. So in the username, we've got hexadecimal node ID. This is a node ID, this big hex number. Then we've got an IP address, port, and discovery port is the same. No, there's 2 ports. Okay, so this node record said it had 2 ports. So already sort of like here it's coming up already. Don't know why. We've got a normal port and then we've got a discovery port. And there it is. The TCP listening port. So maybe that's the first one where you send like a message to start with. And UDP discovery port where you like stream stuff maybe. Who knows why. The enode URL scheme is used by the node discovery protocol and can be used in the bootnodes command. I don't know what the bootnodes command is yet. What is an enode ID in Ethereum? Hudson Jameson. He's a big deal, apparently. Hexadecimal node ID is username portion of URL. Yeah, got that. They said that already. 512-bit public key. Used to verify communication came from a particular node. So it's just literally just sending a public key. It describes an Ethereum node in the form of a universal resource indicator. Is that what URI? Resource identifier. Okay, so they keep saying that. Yay, they've got a hexadecimal node ID, which is a public key, and then that has an IP address, a DNS name. No, DNS domain name is not it. Again, they say that. It came up here. He just copied and pasted that. Is that a link to it? Anyway, cool. So that's just a URI. That might be an easy place to start. What's in enode? Enode. Little. Damn it. There's lots. They're all relatively small though. All right, let's start with this node. Maybe ID scheme. Nah, node. Here we go. Vim node. What have we got in here? 200 lines. That should be manageable. Every node has an ID and a record. And a record is an ENR record. So we've got our new function, so we just create a new one. Must pass, which would fail if it doesn't. So you get given a raw URL, which is in our enode format, and we fail it. Easy, easy so far. Peer-to-peer, not hard. 2 seconds into it. We pass, decodes and verifies the base 64 encoded node record. Returns ID, returns the sequence. If it's incomplete, it's true. So they're just boilerplate to let you play with it. Gives you the IP address of the node. Gives you the UDP of the node. UDP port, TCP port. So there's 2 ports. Still not sure what the difference is yet. Returns the public key of the node. And a record. It gives the full record. Validate complete. Checks whether it has a valid IP. So you've got some validation, string representation of it. Marshal in to put it into JSON files, I guess. ID is a unique identifier. And it does something similar for that. Because that's just 32 bytes. Which I think, and this is all to do with that ID, converts a hex string to an ID. But that first node structure has an ID, which is just 32 bytes. And then there's ENR record, which we haven't found yet. But I guess that's got where this guy is talking about it. It's got their IP address, 2 port numbers. So I guess we have this, which describes everything that will need to go into this Ethereum node record. E-node URL format is used to create an Ethereum node record. Maybe. Cool. So that's node. Didn't give us too much. What's in this ID scheme? ID scheme. Nope. .go. 160 lines. This is what I like to see. Valid schemes. Nah. This is gonna say like version 4 or version 5. No, I don't think I've got enough knowledge of this to understand what's going on there yet. What else we got? Local node. Local node produces the signed node record of a local node. Where's a signed node record? A node run in the current process, setting Ethereum node record entries via the set method updates the record. New local node. So I guess this is just like if you're simulating it, maybe? Nah, uninteresting. Let's not dig into that yet. Node database. What's this? This has got actually some lines in it. Alright, so immediately we're talking to level database. So maybe this is us saving our big list of Ethereum node records, because that's probably going to be important. We've got our DB structure. So this is just wrapping around this level database file here with an ability to quit it, I guess. So like some threading stuff. So boring open-ended database equals .open path or whatever, I assume. Didn't really look at that one actually. New memory database, same thing, but we pass in no file path, instead pass in nothing. So for testing. Persistent database creates and opens a level database backed in level database, I guess. And that's going to call new database, or it just does new database here. Node key. So we've got node records and we've got a node key. So it takes a database node prefix, puts a semicolon, DB discover root. So first of all, what's DB node prefix? Can we get that out of anywhere? It's an N. So like key value sort of databases are really just like a map or like a hash, depending on what language you're using, I guess. But it's just got a key, and you type out some string as the key, and then you put a heap of data into the value. So they make these keys unique, and they start them all with this prefix, so you can do like a search and you say just return everything that's like got this prefix, and just makes it a bit easier to search because you filter your level database by iterator, level DB iterator. It's like you can just go, hey Mr. Database, give me everything that's got this key prefixed by, in our case here it's an N, and then you'll know that everything you got is a node record. None of these is helping. Level DB Golang. Cool. So like exactly here. That's our iterator. iterate over a subset of database content with a prefix. So you've got your level database. You say, I want you to return me everything that's got this prefix. They've typed foo here. We'd be putting n, and it would spit back this iterator, which we can loop over. And that would give us, we just can go through every node that we've got. And then when you want to like say, hey, look, I want to broadcast this to everyone, you can just go through this iterator and it's like your outer loop. So if we go back here, we've got a prefix. You got the n, and then you put the ID. So it's the node prefix colon ID. No, the prefix has it. So this prefix has a colon there already. That's why it's not there. Then we put the ID, which we pass in the ID here. Then we put another colon, and then we do this db discover root. I don't know what that discover root is. v4. Okay, so they're just tagging them as well. So we saved the values into the level database, and they have a value of this like n colon key colon version 4 or version 5, depending what it is. Then we got some functions here to reverse that. So we take a special created thing and can spit them back out with ID, item, and whichever version, I guess, probably is important there as well. Node item key. Okay, so this is sort of all just like, hey, how do you format the items? IP net.ip returns the database key for a node metadata field. I'm not sure what that means. Node metadata field, I don't know what that is right now. I'm assuming it's got some like special meta, unsure. Split node item key. The reverse of that, I guess. Version 5 key takes an ID, the IP address, and the field, which is a string. And they're joining them all together to return something. They're more keys. This is all to do with keys. Fetches an integer associated with a particular key. Interesting. What's the integer represent though? So we store an integer in a given key. We retrieve an integer. Why do we have integers? Unsure right now. Storing uints. Fetching uints. Okay, so maybe they're going over everything. Here's a bit more I thought. Retrieves a node with a given ID from the database. So if we go back into our node, P2P node, what was that file called actually? Node. So we are saving potentially this directly into our database. We've got our like scheme to define the keys, and that's got a big list of these nodes, which has another copy of the ID, I guess. And it's got the Ethereum node record in it. So we've got some insert, retrieve, update sort of boilerplate. Not sure why a record sequence would be used in this case or what it does. Delete nodes, delete range. So we've got, here's our new iterator we were talking about. You go find a prefix and then you delete them all. Like, it just makes it easier to delete all of your nodes. Ensure expiry. So I guess we've got in our list, our nodes are like timed. So we assume they go bad unless they're like refreshed. And then this probably just like iterates over everything and checks them. And if it is checked, it deletes them. Expire nodes. Tick equals new ticker. Tick stop. So this is going to just be set in a timer of some form. Time.newTicker. DB cleanup cycle. How long is it? Every hour. So the nodes expire after being in there for 24 hours, but we do a cleanup every hour. Interesting. Well, what do? We go through, here we go. Here's that exact code. We go through our level database. We get an iterator so we can do a big loop of it. Here is the loop. We search our DB node prefix, which is just the n colon that we had up there. What was it? Yeah. This is our prefix. Everything in our like level database is named after that. So we go find everything that's got that prefix. Get our iterator. If iterator, if not next, then we return. So if it's got nothing in the database, we ignore it. Fun stuff. We've got a threshold, time.now, add an hour. At end equals false. So we start off with an infinite loop. We just set this loop. So split node item key is the key of our iterator. So we've started our infinite loop. This iterator.key gives us the first item in that loop. And as we go around, we'll call next on this iterator to get the next one. So we start here, and it gives us a key, and it's saying split node item key. Gives you an ID, the IP, and the field. So, okay, so maybe I was incorrect. There's an intermediate step with this split node item key. This node item key is actually what stayed as the key. And this ID was what we were talking about the prefix before, I guess. So maybe it takes it and concatenates the IP address and whatever field is as the key. The field is DB, if the field is DB node pong. I don't know what DB node pong. If time, so it gets the value of it. DB node pong has the time in it. If time is greater than the youngest pong. If time is less than threshold, we delete the range. Oh, interesting. So our ID is the start. We've got our N and our colon. Let's just do them here. So like our prefixes, I thought it was just N, whatever, some key, hello, and then like V4. That's what I thought the keys were. But that is just the ID, which is this first field. then they've got this node item key, and I assume they're doing something like adding 192.168.1.1 or something as like the IP, and then they've got field, which is going to be some prefix for db node pong, and that's actually what the key is. So you take this ID, you take the IP address, and you got this field, and then they're saying that db node pong is perhaps what's called for the content. So it's like maybe that equals 100. So it's like there's the key, there's the value, and you look at what this field is to determine what is actually in the database. And if it's db node pong, that gives you a timestamp, I guess. So if we go look for db node pong, last pong, the full key is this. ID v4 IP find fail. Find fail last ping last pong. Interesting. So I guess ping pong here means like you send a message to someone, which is a ping. You save the time that you sent that, and that's what's going to be in here. So if I sent it at 2 p.m. and that's ping, not pong. So what's this? It'd be like last ping. And then down here, when they reply back, you've got last pong, and that'd be like 3 p.m. And then they go through, and if the youngest pong, if the time now is greater than the youngest pong equals now. So does that update it just when it's looked at, or does that look at it when it's... I'm not sure what that does. But here, this time lesson threshold, this is kind of more what I was expecting. So it's like if you say that I want to delete everything that ponged before 4 p.m, you go through it and you delete the range, and they're passing this node item key with this here. So it'd be like, hey, go through the database and delete everything that's got this. So you would delete the last ping, you delete the last pong, plus whatever else is in there. That's the sort of, I guess, the benefit of prefixing everything is this last one, you can have multiple things and you can delete them all by doing this. So we do that, we go over iterator next. We get our split node key. We get the key out of it. If we are at the end, we've moved beyond the last entry, remove everything if there was no recent enough pong. We've moved beyond the last entry of the current ID. Remove everything if there was no recent enough pong. Okay, so that's not that complicated. I feel like details are kind of unimportant here when I'm doing high level sort of digging. So they got pings, pongs, some other things. Let's go back up here to this node, split node ID or whatever it is. So maybe this doesn't actually have the Ethereum node record in it. It's just storing like the pongs and pings so far. So node key is what we looked at before. That generates a key with whatever the unique ID is. I'm assuming it's that hex that they're talking about here. Probably that one. Possibly that one is probably a better way to convey my confidence in that. So you've got that key n:key version 4. Then you got split node key, which takes in this key, this just is like a head over it. So it's like you pass in the key and it gives you this ID and it gives you the rest. So it's kind of like you can recursively look over it. Node item key gives you the ID, so this one up here, the IP address, and this field. And that field is like the, I guess like a command or like a descriptor. No, so this is the other way around. So you pass in the ID, you pass in the IP address, you do that, and it passes you a big byte or a string. Makes the ID node key. Join all those bytes together in the field and end it with a colon. Cool. Less interesting. They're just colon in a heap of stuff together and using that as a key. We got last ping received, so here's some functions to go over. You pass your ID and your IP address, and it will go find the last ping by adding the ping sort of prefixed, which was just last ping. And they do that same thing. It's like update, you pass a time. So like go find that one and then saves that time in it. So we can update our pings, we can update our pongs. Find failures. So I guessing this is just keeping track of how many times you like ping a node that you think is on the network, and if it fails, it'll be like update find fails. I mean, that might be semi-interesting to look into. Update find fails. So there's our definitions. Here's a test, so that's ignorable. But in our discover, when we do lookups, I guess if you don't get a response, 150. So when you do a query to a node, you first of all find if that node has failed. You query the function, and if it fails, you've incremented it by 1 if it fails. So it's like you call it if it gives you if it's error closed, it does this. Else if length equals 0. You avoid recording failures on shutdown. Else if fails is greater than 0. It counts consecutive fails. Okay, that's interesting. So it doesn't keep track of them over a period of time. It's just saying, hey, look, I've pinged this guy, he didn't respond. Immediately send a response back. Failed, count it twice. I guess if that fail gets over a certain point, then you like chuck them out, say you're useless. But if you do get a positive one, this is the first thing that get called, and if it's above 0, then you reset it. So avoid recording failures on shutdown. If it's error closed, then they don't want to because it's someone trying not to. Add seen node. So it means you do find them. Interesting. Cool. So we keep track of how many times they fail when we start querying them. We're keeping track of when we send messages to touch them and say, hey, look, are you there? And if they respond back, we keep track of when they last responded. We keep track of how long they have not replied for. Like if we query them 4 times in a row or something, they don't respond to any of them, we want to chuck them out after 5 times of doing that, I guess. Update find fails is something similar, I guess. Here's version 5 popping up, which could be interesting because everything sort of seemed like it was version 4 in this node keys. Retrieves random nodes to be used as potential seed nodes for bootstrapping. I thought seed nodes were hard coded. We make an iterator with nothing. So for the length of the nodes, we need n nodes. Seek to a random entry. So we just circle over until like we find n number of nodes. So say you want 5 nodes, start at 0, add a random number, blah. Start at that number, add another 5. Add 6 is less than n times 5. 6 plus plus. These are just going to be random elements. They're like randomly finding stuff. Semi uninteresting. Skipping over other database entries. So we do actually store the nodes in this database. But we store the nodes and we also store like pings, pongs, and fails. So when we want to find nodes, we go over the iterators and we ignore them if it's not db discover root. So db discover root must be the prefix for maybe not. That's just version 4. So it's just saying it must be equal to version 4. Must decode node is what? Maybe it doesn't have a prefix. Maybe it not having the prefix is the where it gets stored. So if it doesn't have the prefix, like that field split node, it's the actual node record. Whereas if it is got a after prefix or whatever, then it's I'm not understanding something there. Must decode node is just forcing you to return it back, and it'll give you an error if you don't, right? There's an error there. It panics. So this split node key So we've got this, and then we've got the DB node prefix. No, lost. Why am I lost? We get the ID and we get the rest. String rest. If string rest does not equal DB discover root, continue. Which I thought was just v4. And I thought the split node key. Okay. So we've got node key, node item key. Still got it. If the rest does not equal DB discover root. So you've got, cool. Okay, so this kind of makes sense. Vim. You've got your node root, which is your n colon, insert, n colon 1, 2, 3, 4, ABC. There's your hex. You got v4. And that will equal your Ethereum node record, whatever. But you've also got this n colon 1, 2, 3, 4, ABC, v4. Then you've got your IP address 192.168.1.1. And then you've got your ping pong last ping equals 100. So what this does here is it splits your key. It iterates through everything in a database. So it'll give you both this and this. And then it will split it. And it will split it right at this point here. And you'll go, if the rest, so if this equals version 4, you know you've got the node, which is what this one. If it's not just version 4 and it's got all this garbage too, then you know it's not the node, and you just continue on and you do this loop and it returns every node. Cool. That sort of makes sense. Let me out, please. All right, so back here, and we just close the database when we're done with it. Interesting. So we keep our Ethereum node records. We've got these keys. They're not stored according to this enode format. That's just for like communicating at some point, which we haven't got to yet. So let's get out of here and let's go into Ethereum node record. And yes, here we go. Here's a nice sized folder which doesn't have heaps of stuff. As probably suspected, this ENR is the bigger one. Entries is probably... Actually, I have no idea. Why is there entries? It's not a table, is it? It's a structure. And we've got this test, which you can ignore, I guess. So vim ENR.go. And also, let's get entries up as well. So this seems like a lot of boilerplate. An entry is an ENR key. This satisfies the interface. Cool. So maybe this is going to be an interface and the entries is like the implementation of it. Maybe. Cool. Here we go. Here's an Ethereum node record, I suspect. It just says record, which you kind of assume record represents a node record, being the Ethereum node record, possibly. There's a key value pair in a record. Oh. So each ENR contains a key value list. Why do you have a key value list? What is in you? I don't understand. We've got an address, we've got to verify that it's right. We've got an identity scheme. Nope, no clue what you're doing so far. Set sequence. Nope, don't know what that means. Load retrieves the value of a key. So we go into a record and we can look at keys and values. What is in those keys and values? It might just be a generic structure. Returns the signature of the record. Encodes RLP. Maybe this is just like a generic way of digging into what, because your list of your nodes that are on your P2P network, like you want to keep a bunch of information and maybe you frequently want to add to it. So it's just like they've just defined this key record sort of structure instead of saying, hey, look, we need to know your IP address and we need to know all this stuff. We'll just make it a generic key value and say, look, if we want to come back later, we can dig into it. The components of a node record are a signature, a cryptographic signature of record contents, the sequence number. Nodes should increase the number whenever the record changes and republish the record. The remainder of the record consists of arbitrary key value pairs. It sounds exactly like what's happening. Record signature is made according to an identity scheme. The identity scheme is responsible for deriving a node's address into something header table. Distributed header table. What's exactly that mean? Distributed hash table. The distributed hash table helps you locate resources. Interesting. So the identity scheme is also responsible for deriving, so how we make the hash that goes into the header table. Distributed hash table, not header table. Keys, value pairs, and is a semi-big long list with IP address, TCP port, UDP port, IPv6, TCP, UDP. A public key, which is probably useful. So yeah, they're just, instead of having this Ethereum node record here, it'd be like so many records. I should probably read that header stuff actually. These pairs, it's like this record here could have IP address, IPv6, port, and like everything you want to know about that. But instead they're just like, hey, we define them as pairs, which is just a bunch, which is smart, I guess. And then they define it here, which is this entries, I guess. So we've got an ENR key is a string. So we have to define for every one of these, this entry is a like interface. So we've got to define it. We've got to tell them how to encode it and how to decode it, which is nice. And then down here is them defining them all. So we make an ENR key. Function V returns TCP. What is V? Value. Right, okay. So this is them actually defining all of these. And they do so by defining the return type. No, they're defining the structure. So somewhere in our code base, we've got a TCP structure. We've also got a UDP. And we're defining this new function over that TCP structure called ENR key, which means that we return the key name that this should go in. And that would help us, but not entirely do it, implement this. No, it does. It entirely implements this interface. If you have ENR key on your structure, it just defines the key that needs to map up to your structure. So I've defined a TCP. I know I want to say that in my key value pair in this ENR key. So all I do is I return this TCP string, which defines them all. And then we go down here and it goes through for all of them, for ID, UDP, blah. A little bit more complex for the IP one, I guess. And it's got some special RLP encoding for the IP address. And IPv4 is complicated too. IPv6 is a bit more complicated. And that's the end of our file, I guess, with some stuff for errors. So all this does is this defines these, what's it, 8 entries that go on a ENR record. And they got this signature of the record context. So all this stuff is defined by you. If you want to participate on the network, you start by sending out to the network who you are. And to do so, you must pass all of these, I guess. I don't know where. And you've got to sign it, say this is who I am. And it probably should match up with that. And every time you update it, you've got this sequence here too. So it's like, hey, look, this is a new one. I've changed my IP address in this table. You have to look at the newest one. And then they just sort by newest. Cool. So there's not too much into that. Wait, all keys except ID. ID is the name of the identity scheme, version 4. Oh God. Everything is optional, including IPs. A record without endpoint information is valid as long as its signature is valid. If no TCP6 or UDP6 port is provided, those two ports are applied to both. It should be avoided but doesn't render it invalid. The canonical encoding of a node record is an RLP list of signature, sequence, key value, key value, key value, key value, etc. The maximum record size is 300 bytes. Details, details. We should reject stuff if it's bigger than that. defining the content being the sequence, key value. We sign that, and then our record is the three of them. The textual form of a node record is a base 64 encoding of its RLP representation, prefixed by ENR. Interesting. Is that what this is? No, eNode is different. There we go, that's a very nice thing to have. Doesn't require consensus. We don't have to do a hard fork if we want to know whether or not that this table, we want to add something new to it. Say maybe we want to know what version you're running and we want to chuck that in there. So you wouldn't need a hard fork to do that. Great. Great stuff, guys. Existing clients will accept any key value pairs regardless whether they can interpret their content. Yeah, okay. So, as long as it's less than 300 bytes, you can add whatever you want in there. And even if you can't understand it, you got to ignore it because someone else might be able to. I don't know what identity scheme is in this case. Identity schemes. So this is where they're saying the identity scheme here. A record signature is made and validated according to an identity scheme. So you define version 4 and then you run version 4 records according to whatever this other one is defined as, which probably should have those ones. Where is version 4 defined? I do not know. Cool. So we've got these ENRs. We know how they're stored in the database. I don't want to save you. What else have we got? Node state, interesting. Discover is also interesting. Simulations sounds like something I can probably ignore. Maybe it's a unimportant thing, like a test sort of thing. There's test in. This is what I like to hear. Oh god, this is huge. Read me. Dev peer-to-peer simulations. Yes, cool. Very good. This is all stuff to like do test in. This whole simulations folder. So we can render it uninteresting and not going to look at that. I mean, it'd be pretty cool like to design it. Like you build your own peer-to-peer network structure. You're like, oh yeah, like every person must have these records and send them off and they send messages to each other. And then we like simulate it locally. Cool, great, good thing to do. Not helpful for us learning it though. RLPX might be the base layer of it. But this node state could be a bit more interesting. 1,000 lines, you reckon? There's our 30 kilobytes. All right, what do we got? A node state machine implements a network node related event subscription system. maybe it means that someone can like take what's take what messages you're sending and like save them somewhere, or like if they are according to like a certain format, then it tells everyone what's happening, I guess. So you connect, and then everyone who wants to know when there's a new connection, like the functions that want that, will receive it. So the caller adds timeouts. Bugger. This I think we're not ready for yet. Contains a list of flags by applications. Node info has an enode node, which is our ID and our enode record. So we've got another node sort of info structure, which just contains the node, the Ethereum node record itself, and a bit mask of what its state is. And I don't know what the states are exactly. I'm assuming this tells you how to encode it. This is like if it needs updating in the database. This might be passing on field count. Maybe that's related to the entries. Maybe they're doing something similar here. So we've got this node info structure, which is it keeps everything we've got from the network in these Ethereum node records, but then it's also got our information that we're recording about them. So we're like, oh yeah, this dude is a bad one. So is bad. Like there's an interface, like a Boolean field that says, is this guy bad? Like he's a malicious actor, yes or no. We define that index. We don't want to listen to what they say. They'll tell us everything we need to know here to contact them. But then we're keeping stuff ourselves about it. So this fields is probably going to fall into this like same sort of category as it's like. And this is really nice actually that Ethereum does this. It's like you don't encode those sort of things into the protocol, because if you want to change the protocol, then you need a hard fork. And when it's relating to peer-to-peer, it's almost just like, hey, look, we just define the version that we want to listen to the peer-to-peers from other peers. And if they don't comply with that, then we reject them. And it's just like we ignore their blocks. And it doesn't need a hard fork so much as it just kind of like updates the protocol. So here's a field info structure, which I assume we're going to define a heap of fields that go onto our... So this might actually be the meat, this node info. And our node maintains a big list of these node info fields. Somewhere. Actually, I think I need to dive into the peer-to-peer layer rather than just like a general search. But actually it looks like all of them anyway. I want to see if there's something called like an array of node infos. PupEth does. I think this will be on Node actually. Damn it, where is it? node infos. If it's all in puppet, I'm not going to be puppet. Damn it, it's all there. Haven't found it. I can do this. Damn it. Regex. Nothing. That might just be bad programming by me not being able to search well enough, because there's got to be something. This is a structure that contains information for one of your peers, and we are going to want to maintain a big list of them. Interesting. Bitmask offline state. So in our flags, we have a state is one of the more is this, you got a node, it's got a state, and you got fields describing stuff on it. So this state is probably the most important one, because you want to know if it's up, down, left, or right, I guess. So in this first state that it's saying, like offline is a special one. I don't know why it's special, but bitmask of all ones, I guess. Or bitmask of one. Is that defined in here? Just an integer 64. So it's just 0, 0, 0, 0, 0, 1. Offline. And cool. So in here, we create a new flag state. So they're dynamically creating all these different states that you can have. So offline is the most important one, so it's hard-coded. But I guess it's like, you define a state, has replied to you in the last 10 seconds, maybe. Maybe is not responding to pings or something. I think this might be all like, this is all sort of related to like, hey, we're building this dynamic list of flags. So if we got, we've got our bitmask, which is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And we know that this very first one means it's offline. But then it's like, you as the programmer have to define what that flag is, and you do that for like every single bit here, and that's dynamically built. So it's like, I create this one and I define it to be this, and then you apply that to the bitmask, and yeah, so they're programmatically building their bitmask sort of stuff. Cool. List of names of flags associated. So yeah, can convert from your like zeros and ones into a list of stuff. New node state machine. Create a new node state machine. Persistence can be enabled or disabled for each state, flag, and field. So I'm guessing it's keeping track of the nodes in each type of state that they're interested about. So it's like, if you enter the like online state, you maintain a list of those nodes. Maybe. So you define a heap of states. And then I guess you can move between them. This state mask has a state. Set up clock DB node key. So I'm not sure if this represents a single node or if it represents a bunch of nodes. Although that is very indicative of it being like a bunch of nodes. So there's my array that I was searching for. So this node state machine, I'm assuming there's multiple of them. So you maybe think of it as like an array. So you've got this node state machine 1 equals, you know, a new one of these. So you call new state machine, whatever, blah. And in it, it's got this mapping of enode IDs to node infos. So kind of, this is where I thought it was going to be array, but it's not. It's like an array of node infos, but they've just made it a map. So it's like you can go, you know, enode ID to node info. So you just got, and you say that this is defined as, I'm not sure if it's defined for a single state or if it's just ones that are maybe contain this field. These are all pointers, so they should be like relatively easy to like throw around. Setup.fields. So you'd be like, if fields is got an array and it's offline, not responding, then you've just got this list of people who are offline not responding, and then as they like come online, you would take them out of this one and you'd say, in this machine, this is when they're online, and it's like, hey, look, I move from being in this one to here, and then we've just got a bunch of these like node state machines to watch. And then you go, hey, look, I want to send a message to everyone who is online and responding, which is not this one, but some other one is. Then you can just iterate everyone who's got this. Interesting. So we've got our node state machine structure. State mask has a bunch of flags. So this flags.setup, node state machine setup was here. Is that a, what is a setup? I'm assuming it's just like a, why is that there twice? Node state machine struct. This is at the very top. Why is there two? Node info, node info. Ah, new node state machine. So this is just creating the new node. This definition was at the top. Anyway, so what's setup then? Setup is a version, flags and fields. Flags are name, and if they're persistent, fields are a name and an unknown type, generic, maybe. And then they've got encode and decode functions on them. Optional node field for a given type. So you've got a list of flags. Is that what it is? Setup has a list of flags, yep, and a list of fields. And then that setup is in our node state machine that kind of describes what everything about this state is. And then we've got our big list of node infos in there and some mutex stuff. And then how to store it in the key value store, which I assume is just all that one big level database structure. So we've got our state machines. We go through them whenever we want to like find some nodes. Now somewhere I guess is another structure on top of this that maintains our state machines. So I don't know where that is, but this is going to be boilerplate for a little bit. You know, get the state mask, get the field index. You know, we find a field. So you put in the field and it returns an integer of where it is. And state mask returns its internal one. And it checks if it belongs to it. Subscribe state. So this is interesting. So I guess it maintains a list of people who are subscribed to this state. So if people join or leave it, they'll get notified. Like a callback will happen when that happens. Ooh, or maybe it's just that's when a state, and that's when a field. New node takes an enode node called n, returns node info, new node, fields of emptiness, and length of ns.fields. So it makes an empty structure for it. And where does new node get called from? Decode node. Is that it? Set state, set field. Cool. So these are more just like, that's a helper function. It doesn't do anything. It just takes this enode node and chucks it in there, and then later on they'll define what the fields are, I guess. Check if the state machine is started. So boilerplate, starting. So it's kind of like a service that you enable state and field operations. So maybe those fields are like functions you can call, and when you press start on it, it'll like it'll call those functions over all of those nodes that are in its list, which would be useful, right? It's like, hey, look, I'm shutting down. Call the shutdown message to everyone that's in there, which might be what that field is, maybe. Stop is, so these start and stop are just like at the start of, you know, when we spin up a node itself, it'll be like, hey, start up the state machine for being online and being offline. Load from database, more boilerplate. It's like, go into our level database, get that iterator. Here's our prefix, db node key. So each node state machine has a unique db node key. Slash new state, node state machine. Slash new node state. And that's all that exists in here. New node state machine. I think there's going to be a bunch of them, right? node stats test. Tests can be ignored. Light Ethereum is client pool, priority pool. Interesting. I think a client pool, server pools. So I'm not sure if client pools and server pools in that case are like another wrapper. So you have different types of client pools and different types of server pools, and they all contain a node state machine. And that node state NS is probably what's going to be like this prefix that goes into the level database. NS seems to turn up here a lot. Interesting. So if we go back to where we were, we're gonna have multiple of those state machines, and they send messages to people when stuff changes, and they can call functions possibly over all of the nodes that exist in it. So it's like, please tell everyone in this state that they need to, like, you know, shut down or something maybe. Save node. So you pass in an ID and a node info, and you're just saving it. Like, that's boilerplate. You know, it's just adding items to this node state. Delete node, save to database, update enode. So this is like if the message, if one of your peers has updated this message here, they've say I've changed my IP, they would change that and they would update their sequence number. So you pass in this new node in, and you'd say if this sequence number is greater than what's currently in the node, if node.sequence is greater than node, so your namespace, your node state nodes ID, so you look at what you got in your database, and if the sequence number of this new one updated is greater than it, because they've updated it, you say the node equals this, dirty equals true, which means at some point in the future you have to save it to the database. And you do so by calling persist, I would imagine. Set state, when you start this state machine, you're just going to define what the flags and the... It's all in flags. The state is flags. State subscriptions is people who are listening to that state. There's two set states there. One's public and it's set state, so it calls this. And this is all kind of boilerplate still. It's like, hey, we've got a state machine, it needs to do things. Like, you need to be able to add people to it, you need to be able to like remove people, you need to define what that state is. So it's a really generic, high level sort of like definition. Operation calls the given function as an operation callback. So this probably is where you're saying, I would like to call this function over all the users, not users, nodes. So you define a function and you pass it in the function here as a parameter. And then you lock the database. You say you're doing operation start, which is maybe a time. If not started, then we say it's closed. Call the function, call operation finished, call unlock. So you define a function to go over your state machine, and you call that, and you do whatever you want in this function. It's just wrapping it so you can call it with access to, I guess, this namespace. offline callbacks. To call at startup or shutdown. Add timeouts. I'm not sure what you'd do with timeouts in this case. Maybe you were just like going through people who are not responding and you move them to offline if they're not, like if a time happens, I guess, but get field retrieves a field. So this is all boilerplate. This is getting less interesting. The meat of the function is purely in this, like the fact that you've got a state structure, and that state structure defines like something about it, some like definition, and then it's got a big list of nodes in it, and you can call functions over them. Like a login. I want to log when you come in and out. And I think I might call it at this. This is a pretty good start to like the peer-to-peer layer. Like eNodes, ENRs, and node states. Like they're going to be the meat of the structure. And then it's just like the rest of it is probably like when you start up, please call their seed nodes and then populate these databases and move them into the right state depending on who they are. And then you get messages from people and do actions according to it. But I think that's a good place to call it. And I'll dig further into this in a few more. I suspect this will take a couple videos to get through. Cheers, guys.